and things. All right. I should have those exams, the short answer portion graded this afternoon. It's kind of my plan when I'm done teaching to knock all those out for you guys. And then get grades reflecting kind of the different percentage weights for each homework type as well as the exam. I'll probably treat the exam as though it's your best exam, which looking at the scores, that probably gives you kind of a best case. I mean, it's probably going to end up being most of your best exams. Honestly, the grades tend to be a little lower on the second and third. So I'll get those updated today before I head out. So just kind of to jump back where we left off last class and kind of do a little bit of a quick review of some of the things that we talked about. And then we'll keep using that standard normal table a little more today as well. All right, so we talked about, we have these normally distributed variables, and that if we can somehow get a standard normally distributed variable with these z-scores, our life becomes a lot easier because we can use that table where someone's already essentially done that cumulative density function for us, right? We could look up a z-value in the table, and the table will tell us the probability we see that or anything below it. So we have a normally distributed variable. We want to turn it into this standard normally distributed variable that has a mean 0 variance of 1, because then we can use that standard normal table to help us find different probabilities. Right? That's kind of where we left off. Right? So typically, instead of thinking about, if we have a variable x, I don't, be very surprised if we could find something that naturally occurs of having a mean 0 and a variance of 1. So usually we're thinking about this is our z-scores down here, right? That is standard normally distributed. So how do we get those z-scores? We said we take whatever value we're interested in finding the probability of seeing that or anything below it. We subtract the mean, divide by the standard deviation. That gives us a z-score. We can then look that up in the table, right? The z-score reflects, right, the number of standard deviations away from the mean that x value was, right? So typically we see something like 70 for x. We then, maybe that's something like, I don't know, height in inches. So we then subtract average height, divide by the standard deviation in height. We now know how far away from the mean, how many standard deviations away from the mean that x value of 70 was, right? Once we convert it to a z-score. So if the z-score is negative, that's being below the mean. Positive, above, the value represents the number of standard deviations away we are in either direction. And we also, just kind of a reminder, we said the mean will always have a z-score of 0. So if we plug in for x, the mean minus the mean is 0, we get that z-score of 0 for the mean. Okay, so these z-scores are standard normally distributed with a mean 0 variance of 1. So this is what we want eventually. I think I have this. We did a lot of this last class, but right, I mean, a z-score of 1, you're 1 standard deviation above the mean. Z-score of 2 would be 2 standard deviations below the mean. Just kind of a quick recap of where we left off. Okay, so what happens if we start out with a normally distributed variable and it doesn't have a mean of 0, it doesn't have a variance of 1? Well, that's almost every single time, okay? And then I might say, okay, what's the probability that for this random variable x, I see it take on a value in between a and b, right? So this could be, I select a person at random and I say, what's the probability that their height is in between 65 and 70 inches, right? And that would be my kind of a and b values, right? Well, I can't look up 65 and 70 in that standard normal table. In fact, it only goes from like -4 to 4. Well, that's because these values are for the original variable x, not converted into z-scores. So we need to take those two cutoff values, transform them into z-scores, right? So I'll turn A into a z-score. I'll turn B into a z-score. And then I think about what region am I looking for? Well, I want the area in between those two values. I can then use my table to find the probabilities that I would need to find whatever region I want. And I'll work through an example, and I think these steps will make a little bit more sense here. And this fourth one, some transformation. Sometimes we have to do a little bit of some basic math at the end. Once we have our probabilities, subtract one from the other or add them together, depending on what exactly we're looking for. Okay? So let's just work with some numbers, and I think this will make a little more sense. So I've got some variable. It's normally distributed. It's got a mean of 5 and a variance of 25. Okay? Remember, when we write this here as normally distributed, this is our mean and our variance. So what's the probability if I was to choose one observation at random here? This isn't really, don't have a specific example here, just kind of some numbers. What's the probability that random variable x is between 10 and 15? So, excuse me, the first thing that we're going to do, I'm going to draw this out for us. I think you just always start out, just draw out what you're looking for, right? So I've got, you can think about, it might be a little bit high, but we'll deal with it. So I have this normally distributed variable x. I want the probability it's between A and B. My A and B values were what? 5 and 10, I think? No, 10 and 15. Sorry. I'm going to do something else here. All right. So my original variable had a mean of 5, right? And I wanted the probability it was between 10 and 15. So I'm looking for this area, right? Now I could go back to that probability density function, integrate that function from 10 to 15, and I could get that answer. But it's not going to be expected of you. We can use these tables and make life a little bit easier than doing all that math. So right away, what do I know this probability has to be less than? What's the area to the right and the left of the mean? The area under the curve is 1. If it's a normal distribution, it's symmetric around the mean, so the area to the left and the right of the mean has to be 0.5. So automatically, I know I'm looking for something that's smaller than 0.5, right? The entire area to the right of the mean would be 0.5, and so I want something smaller. So what I'm going to do is I'm going to turn these into z-scores. Now, for the mean, I don't necessarily have to put this on here, but I always know it's going to have a z-score of 0, right? From here, I'm going to use my formula for the z-score and turn 10 and 15 into z-scores, right? So for the first one, right, I would take that x value of 10, subtract the mean of 5, and if my variance was 25, I need to divide by the standard deviation, so the square root of 25, right? If I do that, I end up with 1. So I'll map this out. That was a z-score of 1, okay? Now, if I think about this one intuitively, you don't have to use that formula. It helps me when the numbers aren't as nice. But if my variance is 25, my standard deviation is what? Square root of that, so 5. How far away is 15 from the mean? 10. The standard deviation is 5, and this is 10 away from the mean. How many standard deviations away from the mean is it? 2. Now I could plug it into my formula and find that z-score of 2 as well, just like I did up here for the value of 10. But with these nice easy numbers and remembering what the definition of a z-score is, it's pretty easy to see here that value of 15 would have a z-score of 2. Okay? So this is the area that I want. Right? So what I can do is I can use my table to find the area to the left of 1. I can also use it to find the area to the left of that z-score of 2. And if I want the area that's in between, how can I use those to find that? Subtract the smaller from the larger, right? And then all I'll be left with is what's in the middle there, okay? So kind of that subtraction. So I looked at my probabilities. That last final step was like, I have to subtract this smaller one from the larger one. And I think if you draw it out, a lot of the times what you have to do for that final step kind of just makes sense looking at the visual. Right? Any questions on that? You okay with this? So we actually have to look these probabilities up, because I doubt we know them off the top of our head. So if we look up a z-score of 1, it's kind of a little tricky here, but 1.00, right? That's a z-score of 1. So 0.8413. So if I'm thinking here, just for the recorded video, I kind of can have this up here. So this area right here was 0.8413. And then the larger area, we had to look up a z-score of 2. So we go here, 2.00, 0.9772. I'll subtract 0.8413 from 0.9772, and that'll give me the probability I'm in between that z-score of 1 and 2. Okay? So I think I actually have this. Oops, I need to do that. Excuse me. So we turn these into z-scores, kind of plot this. I want the probability in between 1 and 2. I look up those two probabilities. You can kind of see here. If I wanted to shade this in, I tried shading on the board sometimes. I try using different colors and it ends up just looking like a mess. So that's why I kind of draw these large circles to indicate what we're looking for. But you could think about it as the area to the left of that z-score of 1 is this bricked area. The area to the left of that z-score of 2 is this light blue area. Where do they intersect? Kind of just where they, brick and light blue. We subtract the brick from the light blue. All we're left with is what's right here, right? So I subtract 0.84 from 0.97, and I get that probability of being in between those two z values of about 0.13. Questions on that? It's not too bad. Working with some nice, easy numbers here, so it might get a little harder, but yeah.
How do we know that the standard deviation was 25?
So remember, we're told this is a normally distributed variable, mean of 5, variance of 25. So if I have a variance of 25, to get the standard deviation, I would just take the square root. Or kind of as a reminder, right here, this was actually the standard deviation I was dividing by, which was the square root of the variance. Okay. Any other questions on that one? Okay. Excuse me. So let's go. Thinking about some more examples here. Okay. Get rid of myself for a second. So I think I mentioned last class that rainfall is also one of these variables that we see that's normally distributed. So we could look at average monthly rainfall and variance of monthly rainfall, and I have an Excel file with this, so we'll go to that at the end after we work through some problems by hand. But if I had this data in Excel, it'd be very easy to find the average and the variance of this rainfall variable. Now, obviously, we can think about rainfall is going to vary by month, so we could also break this down by month as well, right, and calculate averages and variances. I'll show you this eventually when we get to the Excel file, but if you look at average monthly rainfall for the last however many years, and you put it into a histogram, it looks pretty nice and normally distributed, right? We might have a couple that are a little extreme here, but very close to a normal distribution, just occurring naturally. So there's this big drought in 2012. And I don't know, I put this up there, people working now, not getting enough rain, really, really bad. You can kind of even see, we look at the cyclicality. So I did a time series graph here by month. Notice to February and June, right? Usually we see kind of these spikes, right? It's kind of cyclical, rainfall is cyclical, but then we get to February, June in 2012, and notice that not only did it not spike, it actually went lower than it usually does. And so how likely or unlikely was it that in that year they saw as little rainfall as they did, right? That's the kind of question we can start to answer, right? And you can think, if I'm trying to project things for the future, I might want to know what is the likelihood, right, that I see below a certain amount of rainfall this year, because if I'm a farmer and I know that I need X amount of, of rainfall to make sure I get the crop yield I want, well, if that has a relatively high probability that I get below that cutoff, I'm concerned, right? So let's think about, we have monthly rainfall, and over that time period, the average monthly rainfall they saw in 2012 was 1.3 inches. If we know that on average, monthly rainfall is 3.4 and has a variance of 2.57, what's the probability that we see total monthly rainfall be less than 1.3 inches this year? Actually, I think I might have an error in here. No, I don't. Okay. So we've got this normally distributed variable, and we want to know what's the probability that that variable takes on a value of 1.3 or less. Okay. So for the recorded video, I'll have this popped up, and I think it should be big enough so you can see. All right. So the first thing we always want to start out is draw out what we're looking at. Just to think about, maybe can we bound what this probability has to be? So I've got this variable x, which represents rainfall. I know the average was, what, 3.4? And I want the probability I see 1.3 or anything less. right? Because if I see anything less than that amount of rainfall, I know that my crops are in trouble. So I'm going to turn these values into z-scores here. Now I only have one value I really need to be concerned about. I know the mean will always have a z-score of 0, but I want to find the z-score for 1.3 inches of rainfall. Now right away I know this probability has to be less than what? 0.5, right? The area to the left of the mean would be 0.5. I'm looking for an area smaller than that. So I'll turn 1.3 into a z-score by doing what? Subtracting that mean. And up here, I think I have the variance was 2.57. So my standard deviation would be the square root of that. And that's what I need to be dividing by when I'm finding that z-score. Okay? Everybody with me on up to that point? Okay. Let's see if I make sure I keep an eye on the chat here. Okay. So I turn that into a z-score. Now right away, I should know the z-score should be negative because I'm looking at a value that's below the mean, right? So what's the region I want? We already drew that. So what's the probability from the table? Well, once I have that z-score, I just look up negative 1.31. Go here. So negative 1.31, negative 1.3, and if I can kind of remember, here the column is 0.1, so this is why I said having it in front of you might be a little bit easier. Negative 1.31, 0.0951 is that probability, or that area to the left, okay? So once I have that area to the left, on this one, my final answer, or my final step, is nothing, right? I don't have to transform this at all because I wanted the area to the left. Now let's say I wanted the probability of seeing more than 1.3 inches of rainfall. What would that final step be? So if I instead wanted the probability I see 1.3 inches of rainfall, I convert that into a z-score, it's negative 1.31. I actually want the area to the right. Well, if I find the area to the left, what's the only thing I have to do? Subtract it from 1, right? Because the area under the curve is 1. So if I know what's to the left of this value, I automatically know what's to the right, okay? So that one's pretty easy, I think. I think that one's not too bad. Let's try to work through another example because I thought this one was kind of relevant and interesting. And I'm hoping, did I get this? Oh, I think I made a mistake in here and I didn't catch it. There it is. All right. So let's say we look at September rainfall. So on average, we see 3.25 inches of rainfall every September, has a variance of 2.37. What's the probability that we saw total rainfall last September be less than 0.47? So actually, the reason why I use this value is I looked it up so this September's been fairly dry. I've gotten some rain recently. Last September, we actually only had 0.47 inches of rainfall. And so how unlikely was it that we saw that, right? Well, first of all, if I take the square root of 2.37, that will give me my standard deviation, right? I think if I do that, it's on the next slide, but I think it's like what, 1.4 or something like that. So how many standard deviations away from the mean of 3.25 would this value be? Well, if the standard deviation is like 1.4, we're almost like 2 standard deviations below the mean. So we can start to think this probability is probably going to be relatively small, right? But we can go through and actually, complete this example just like the one before. So I want the probability it's less than or equal to 0.47. I turn it into a z-score. So I subtract the mean, divide by the standard deviation. Once again, this 1.41 comes from taking the square root of the variance, okay? I find that z-score, so it's not quite 2. I think it was kind of rounding a lot of things in my head there, but we're getting close to 2, right? So a z-score of negative 1.81, all right? So first of all, if I think about the example that I just did, right, I had a z-score of negative 1.31 in the previous example. And I found the area to the right of it, and I can't remember the exact number, it was 0.09 something, 58 or something like that. If I now am going to be looking up a z-score of negative 1.81, what do I know that area has to be less than? definitely has to be less than the one that I just found, right? As I move more standard deviations away from the mean, right, or to kind of lower and lower z-scores or a greater negative value, I'm just getting a smaller area in that left tail. Right? So right away, I know this probability is going to be pretty small, or less, definitely less than 0.09. So I go to the table, negative 1.8, and this column is the 1, so 0.0351. Right? So if I go back, we look it up, 0.0351. I don't have to do anything else here because I wanted the area to the left, right? This is kind of interesting. Like the likelihood we saw rainfall be that low, even though the average usually is 3, there's still about a, what, 3.5% chance that we saw that little amount of rainfall. And that's because, I mean, it doesn't seem like a high variance, but when our average is that low, like 2.3, there's quite a bit of variation that we would see in monthly rainfall. Yeah.
Why exactly is it written like that, like mean, variance?
That's just the convention that it's written as. That's just how you identify it. Because remember, if we look back at that probability density function, it's not really like the variance and the mean were what's in there. And so we needed to define this is a normal distribution. And for that density function, you should use this mean and this variance. That's kind of why that is the convention, but that's, yeah, it'd be a little bit easier if they always gave us the standard deviation, right? But yeah, that's why we write it like that. And then it's really just the same thing that we did before. So that one shouldn't be too bad, okay? Any questions on that one before I move on to something a little bit harder? I just thought this was kind of interesting because I was looking at the weather data and I saw it was that low last year. It's like, oh geez, that's crazy. So temperature also is pretty close to following a normal distribution if we look at like in the same location by month, not overall the whole year. So I could look at the average annual temperatures, but I could also break this down by month, right? So what I'm going to do, I think I did a couple months here too. So February, we've got June, obviously different means. You can also see like June temperature, a lot less variable, right, or a lot less variation. If we look at February's average temperature, it wildly swings, right? Sometimes it might be really cold, sometimes it might be, you know, quite a bit warmer, okay? And this is all for Indiana. So let's think about, we have another example. So average June temperature in Indiana is normally what, 70.75, and we got a variance of 6.3. What's the probability this June we see the temperature be 71.4 or greater, right? Well, I'm gonna start drawing this out and I'll switch over to the screen here in just a second. See if I can remember these values. I probably won't be able to, so you guys might have to help me out. So we had what? 70.75. Variance was 6.3.
Yep.
Can't quite see this here. So our standard deviation is square root of 6.3. If anybody has a calculator out and you want to help me out, what is that about? Somewhere between 2 and 3. Yes, I can grab mine. So square root of 6.3, 2.51. Okay. We then said, what's the probability I see 71.4 or greater, right? So right away, I know this probability has to be less than what's the area to the right of the mean? This area is smaller than that, right? So less than 0.5. Now, I need to convert these to z-scores, or at least convert this value to a z-score, and then find the area to the right, okay? So I'm gonna look at this. Before I even compute this z-score, just looking at what the standard deviation is, so remember 2.51, I know my z-score is gonna be less than what value? There's one value that's pretty easy. I can kind of see that it has to be less than. How far away from the mean is 71.4? Less than 1, right? My standard deviation is 2.51, and I'm only 1 away from, I'm less than a standard deviation away. In fact, I'm less than half a standard deviation away here. So I should end up with a pretty low z-score, right? Or a z-score close to 0. Okay? If we go ahead and plug these values in, I'm interested in that value of 71.4. I'll subtract the mean, divide by the standard deviation. I don't have any idea what this is, but I have it on the slides here, right? So let's go back to the slides here and kind of see what that ends up being, right? So 0.26 approximately, okay? So if my z-score is about 0.26, I then want to go and look this up in the table, right? So 0.26, so I'm going to go down here to my positive z-values. There we go. 0.26, so 0.6026. But remember, the table always tells me the area to the left. I wanted the area to the right. So now I actually do have to do something for that fourth step, which is subtract the area from to the left from 1. So what, 0.3974? Okay. What do I want to say? Or something else I wanted to say. Maybe not, I can't remember. Any questions on that before we kind of keep moving? So here we actually had a fourth step. We had to do something. But yeah, not too bad. I don't think this is terribly too tough yet. So, you know, when you think about what the likelihood is, it's about what's the probability that it's warmer than 71.4 on average this, what is it, July or June? June, about a 40% chance, right? Oh, I know what I'm going to say. So notice here we had a z-score of 0.259. We're obviously limited when we use the table to the second decimal. So always round to your second decimal and then look up that z-score, okay? Where are we at in time? Oh, we're good. Any questions on that before we keep moving? All right, that one's pretty easy. We could do the same thing with just some different values. I probably am gonna go through this one quickly so we can get a little bit of look into Excel here. But notice for February, what's the probability that I saw greater than 42.85 degrees? So the reason why I chose this one, once again, this was the 2017 February temperature. So how unlikely was it that it was actually that warm in 2017 in February? Well, we have the mean here. What would my standard deviation be? So I've got what, 26.16. So if I take the square root of that, it's about 5.1. So we can think about our standard deviation here is about 5, right? How many standard deviations away from the mean is 42? Well, more than 2 standard deviations, or about 2 standard deviations. So how unlikely should this be? Well, we're thinking about 2 standard deviations away from the mean, and this is all, I'm just, this is all kind of approximating and doing some pretty wild, pretty irresponsible rounding here. But if I'm about 2 standard deviations away from the mean, well, that's the definition of a z-score. I should be way up here. And one thing I kind of mentioned last class, if we think about what is a high z-score, 2 or more is pretty high. It's not very often you would even see a z-score of 2. In fact, if we look at our table, right, you'll kind of notice, well, I'll do the negative side because that makes a little bit more sense. If I look at z-scores of -3, all these probabilities are essentially what? 0, right? They're all, we're out to the 4th decimal and they're, so if I'm thinking about being more than 3 standard deviations away from the mean, that probability that I'm that many standard deviations away or even further is already really close to 0. And if I look at these, anything over 2, well, these probabilities aren't 0, but they're 1, maybe 2%, right? So being 2 away, we should already be thinking this is going to be a small probability. Right? It's going to be pretty small. Now we can actually go ahead and calculate because we have the numbers, right? We have the mean. We can take the square root of the variance to find the standard deviation. We can convert this 42.85 into a z-score. Right? So we go ahead and do that. We get about 2.73. Right? Wait, why am I? Oh, because this is, I rounded really irresponsibly. That's why it's so much higher than just 2. Right? But 2.73 standard deviations away from the mean. Okay? So I can look up 2.73, but remember that gives me the area to the left if I look that value up in the table. So I'll go ahead, I'll look that value up in the table, 2.73. So here's my 0.3 comp. So I'll keep going down here to 2.7, 0.9968, right? Well, if that's 0.9968, I actually want the area to the right, so I need to subtract that from 1. Okay? So what, 0.0032 here? I'll get out of the way here in just a second. Everyone follow that okay? Are we okay with that? Seeing a lot of head nods, yes. Okay. Kind of the same thing we did with the last example, just some different numbers. But it's an interesting result, right? I mean, what we're saying is the probability that the average temperature in February 2017, the probability it was 42 point whatever degrees or higher, 0.3% chance, right? So that was a like very uncommon February that year, right? Now this is obviously weather data, and yeah, it's kind of interesting to know, but like if you're making decisions, like I was trying to use the kind of crop yield example that are directly tied to temperature, or even if I'm selling goods, right, that I know are going to be more likely to be used if it's hotter or colder, if it's less rainy or more, these are probabilities I want to factor into my decision making. Right? So really, really relevant, really useful. I think what I'm going to do is hold off on the inverse transformation, and we're just going to jump to Excel for a little bit, okay? And kind of give you an idea about, yeah, we can do this process by hand. We can do some stuff in Excel that quite a bit easier, you know, at least I think. So just to kind of show you some stuff, I had, this is where I did my time series. So let's say, I think I did the last like 4 years, so it's probably all the way at the bottom. Yeah, I did some other goofy charts here too, but it was harder to see when I included more years. But I could create a time series graph using temperature here. Oh, this is the other one. This is the one I showed you. I just did kind of the last, what, 3 or 4 years in this data set. Let's look at rainfall here real quick, okay? So I have this set up like this, and this is kind of the completed file that's up on Canvas, but I'm gonna get rid of this so that I can show you how we come up with some of this stuff. So up here, I'm not gonna redo this because this is pretty easy. I just have, what's the average annual temperature, average annual rainfall, and then I did what's the average rainfall in June, average rainfall in July, and the way I did that was, if I have a variable that represents July rainfall, all I have to do is take the average of that variable, right? I then also found the variance of that variable. I treated this as a sample. You know, I have quite a few observations here. It's not going to make a big deal if I use population or sample here, but we don't have every single year of June rainfall, so we should be treating this as a sample. I then have the standard deviation, right? I took the square root. So maybe just to kind of make this a little bit more clear as we're working through this, right? I calculated this for 4 different months and then also for the annual. So I'm going to do the monthly one. It's kind of interesting. So what I'm going to do is say, maybe I'm interested in what's the probability, and we'll do the one we did in class, right? 71.4. What's the probability that it's maybe less than 71.4 degrees in June? Well, I could do this 2 different ways, right, in Excel. And actually, once again, if I forget to zoom, you gotta yell at me. So I first could just use Excel as a calculator, right? Turn that X value into a Z-score by taking that X value, subtracting my mean, and then dividing by my standard deviation, right? That'll give me the Z-score, okay? So hit enter. Wait, did I make a mistake there? Oh, what's in this cell? What's H? Oh, because this isn't temperature, it's rainfall. Okay, we need to choose a different cutoff value. I was going to say, how in the world are we 43 standard deviations away? It's because I'm on the rainfall one. So let's do, well, the average is 4.2. Let's do something like, let's do 3.5 inches of rainfall. Right? Okay, that looks a little bit better, right? We're below the mean, but not too far below the mean, so we get a Z-score of about negative 0.45. Right? So that same equation in there, I just changed that cutoff value that we're interested in. Okay. Well, once I have that Z-score, I can use the norm.s.dist function, And what this tells Excel is, hey, I want to use a standard normal distribution, and I'm going to tell you the value that I want you to find the probability of seeing that z-value or anything below it, which is essentially what the tables do, right? So this norm.s.dist is just like you're using that physical copy of the table, except for instead of you looking it up to the second decimal, Excel, what it really does, it doesn't have a table built into it. It does that integration from negative infinity up to that value, okay? And then it returns to you the area to the left. So what z-score am I looking up? This guy right here. And I don't know why 0 is even an option. If you're using this norm.s.dist, always put a 1 here for the second thing. So what it will tell you is that if you put a 0 in, it'll return to you the value, like a probability density function. But if that's really what it's doing, what should it return to you? Yeah, right? So what it's actually, I think what it's actually doing is like finding you like a really small sliver. I don't know what the bounds are pre-programmed into Excel as, but we're never going to use that because it's not really, you're not really getting the probability of that one value, right? The probability of any one value should be 0. So we're always going to use it just like we're looking it up in the table and just make it cumulative. Find the area to the left, okay? So we'll hit enter there. All right. Now another formula we could use and kind of cut out this middle step is norm.dist. So what norm.dist does is tell Excel, hey, look, I have a normally distributed variable, but it's not standard normally distributed. I don't want to calculate the z-score. I don't really care what it is. I want you to do it for me behind the scenes, then look up that z-score and tell me the area to the left of it. So I will tell, I still have that same cutoff value for x, comma. The second thing I tell it, it's the mean. Third thing, comma, the standard deviation. And then once again, that final thing, cumulative, will always keep as a 1. So it's giving me the area to the left every single time. Okay. If I do that, it gives me the exact same value because it's essentially calculating the z-score without me seeing it, then putting it into that norm.s.dist function and returning to me the value. Okay. And because I have this kind of set up like this, you just copy this over. Now, it filled in these values for me, but I could play around with, okay, what if I wanted to look at each month, what's the probability I see 3.5 inches of rainfall? And you can kind of see in certain months, it's less likely than in others, right? Which one should be, hold on, did I forget to do something here? Oh, because these variances are different. I was gonna say, why is that one so much different? But yeah, you can see the same amount of rainfall has different probabilities of occurring in different months, okay? Any questions on that? Or you wanna see one of these cells again? Okay. And we could play around with what cutoff values, right? I could say, well, what about 2 inches of rainfall or whatever I want there. And I'd have the same thing on this temperature one, so I won't kind of recreate that. It's really just the exact same formulas. So I'll take a quick peek at them, right? It's the exact same formulas. I could turn it into a z-score and use the norm.s.dist, or I could use that norm.dist and just tell it the mean and the standard deviation and have it do all the calculations behind the scenes for me. Yeah?
If you really wanted to, could you integrate with that equation, like that first equation that you were given? Like in the
Yeah. Going from negative infinity to whatever, that's where all those numbers come from. So like if I integrated that function from negative infinity to negative 2.9, it would return to me 0.0019. I mean, that would be the value that you get, yeah.
Someone just like sit around and like.
Well, funny you should ask. Some people sit around and do weird things. So, where did I have this? Right. So I actually did this in Excel, not by hand, but you can actually recreate that table. So here I put, the first decimals. Here I put the second, right? So one thing I don't expect you guys to know how to do, this is probably like if I was just teaching an Excel class, I'd be a little more, I've only taught you how to freeze them. You can actually, if you only use $1 sign, it'll freeze the column, but not the row, right? So here, if I freeze this column, I copy this over, it's going to keep taking A2 and then updating the column, but not the row. So it'll take A2 plus B1. Then when I copy it over here, it's A2 plus C1. And so all I'm doing there is I'm using that standard normal distribution, taking that row and column, whatever they add up to get me that value, and then finding the area to the left. And then I could also copy this down, and because of the way that I froze the cells, it starts to take, it doesn't update, it's not updating B1, but it'll update kind of my A2 to A3 to A4, right? And if I do that, I can kind of see, hopefully, if I did things right, here's a good check. Once I get to 0, hopefully I'm getting 0.5, right? And then also, once I get kind of up to here, I should see things getting really close to 1. Right? So yeah, you could, if you wanted to, and you had a little bit of knowledge about how to play around with the freezing of the cells, you can actually recreate that table in Excel. Now, the original tables, yeah, I assume someone sat down and did the integration for every single one of those cells, right? But I mean, that's one of those things where once they had it all done, well, it's a lot easier than have to do it every single time. You can kind of, go right to the table. Yeah. Any questions on that? I'm not going to expect you to do something like this, but I thought it was kind of interesting that you could kind of recreate and produce your own there if you wanted to. We will, let's see if there's anything else I want to show in Excel. So it's really, it's pretty easy. The two functions you're really going to be using are this norm.s.dist if you have the z-score already. And then if you don't have the z-score, but you have the mean and the variance in Excel, you can just use that norm.dist function instead of using that table every single time, okay? Now, one of the useful things about this, doing this in Excel is I'm not limited to the third decimal, right? So notice these z-scores I've got to, out to whatever decimal I want. Well, I'd have to round this to what? 0.21. Well, if I look up 0.21 in this table, the area to the left of it is 0.5832. So here, 0.5849. So it's, it's not a whole lot different, but if I had to round, I wouldn't be getting the exact precise probability, right? It'd be a little bit off. So in Excel, we're not limited by those two decimals like we would be in the physical copy of the table, right? I guess if we wanted to, you could do like a third decimal and have like a 3-dimensional table where like the third dimension is the third decimal. No one's liking that idea. But yeah, so it makes things a lot easier if we do this in Excel. And it's kind of interesting to play around with this, right? Like, I don't know, what's the probability? Well, actually, we could just copy this over one and get October in here. Oh, except for, oh, I had these all frozen. Why did I do that? These shouldn't be frozen, that's why. Oh, my FN key doesn't work. There we go. So let's do that. So I'm gonna freeze these real quick. You guys copied something over, right? So now let's do this. Now we should get, there we go, now we get different values, right? So the average temperature in October is 66. Let's make sure I didn't freeze these. We can copy this over. October, and say like, what's the probability that this October, the average temperature is 70 or lower? Well, pretty high. We could also like turn this around and say, I actually don't want just the probability of being less than. Find me the probability that I'm actually greater than this temperature, right? And then I could play around and say, well, what's the probability that it's as hot as 75 or more this October? Well, pretty much no chance, right? But you could play around, what about 65? Pretty good chance that it's going to be an average temperature of 65 or higher this October. Whatever cutoff values you're interested in, you can kind of play around with that here, okay? Any questions for me on any of that? I don't think this is too bad. We'll do the inverse transformation Monday, and we'll also start playing around with this exponential log normal stuff. I will, after Monday's class, likely, I'm thinking we'll get through enough material to where I will give you an individual assignment, right? And it will be dealing with the normal distribution as well as the exponential and the log normal, okay? This one is tough. The exponential is not too bad. I'll be honestly, this is not going to be a lot of fun when we talk about it, but it's really useful. And so we'll start that on Monday. So if there's no more questions for me, I'll try to get those the short answer portions graded and your grades updated on Canvas. Other than that, I did put up the next Connect assignment. So you can start working on that. We haven't done everything obviously yet, but you can start chipping away at that. So once you have the individual assignment, you can have at least a good part of the Connect assignment maybe kind of started and not as much work, all in like the last couple days before they're due. All right. Other than that, have a good weekend, and I'll see you guys on Monday. Oh, I saw something in the chat. Oh, will there be an online quiz? Yeah, I'll get an online quiz up there once I get done teaching today as well. Once again, has to be completed before we start class on Monday. Good question. Thank you for asking.